Could you go over the Lie brackets?
Yeah, Lie brackets. Yeah. Lie bracket is a general concept. Okay, so suppose you have an object, an algebra. Okay. So what is an algebra? Algebra is some sort of vector space kind of thing, where there's a product defined. So algebra is some kind of a vector space, or it could be a module. A vector space is usually, is defined over some field, right? A module doesn't have to be defined over a field. It has to be defined over some ring. So, for the sake of simplicity, let's take a vector space. So algebra is some element, some vector space, just one second. So it has some objects, say alpha 1, alpha 2, well, it has an infinite number of objects, right? But so suppose that, even though it's a finite dimensional vector space, you have an infinite dimensional object in principle. So now suppose there's a map, a product. So what makes it an algebra? What makes it an algebra is that there is some product. Okay, there is some product, meaning that some binary operation which takes one element, two elements of the vector space and gives you another element of that vector space, right? That is what we call a binary operation. It's like the group multiplication, but it doesn't have all those nice, you don't assume all those, but you're working on the vector space. Okay, so this is what an algebra is in a very rough sense. It's a vector space with a binary operation defined on it. Okay, do you understand that, Fiza?
Yes, sir, I do.
Yeah, so that operation can be something very arbitrary. Okay, it is very general. You can say, okay, suppose my vector space consists of, say, an orange, an apple, and a banana, right? Or this is the basis. And then you can just say, okay, if I take two orange, I get, say, an apple. And then, you can define some product. All I'm trying to say is that the product can be some arbitrary weird thing I don't care about. It just makes the set into an algebra. Now, if the product is a Lie bracket, so if the product is a Lie bracket, then, we usually denote it like this, and it's a product from Vn to Vn, such that if you take two elements of the vector space, it's skew symmetric. Okay. Okay, it's anti-symmetric product. Do you understand that?
Yes, sir.
That's condition number 2. It's a non-associative product, unlike the group multiplication. Okay, the group multiplication is also binary, but that's a non-associative product, right? That's an associative. Associativity is a very important rule, but this is a non-associative product. So you have to specify how, if I have 3 elements, how I'm going to, what is the rule of associativity, right? And the rule of associativity is given by the Yakubi identity. So if you have 3 elements, X, Y, and Z, and then this particular combination must be 0. So this is called the Yakubi identity. Okay. So when your algebra has a product which has these two properties, it's called a Lie algebra. Okay, that's it. And that's called a Lie bracket. Sorry. Yeah. So this bracket or this product is called a Lie bracket. So examples is the Lie algebra of matrix groups. In matrix groups, the product is given by the commutator, commutator of matrices. And in classical mechanics, in Hamiltonian mechanics, this thing is given by what is known as a Poisson bracket. Okay. So if you take the definition of a commutator, you will see it's antisymmetric and it automatically satisfies the Yakubi identity. If you take the definition of the Poisson bracket, which is a bit more complicated than the commutator, you will see that it's antisymmetric and it also automatically satisfies the Yakubi identity. Okay, does that answer your question?
Yes, it does.
Okay.
Thank you, sir.
Farhan, let me come to your question.